Hey, Geometry Nation. Mr. Mitchell here, room 124. Glad to be part of the nation. I like Mr. Scott's term. And I'm going to take circles a little further today. We are going to talk about inscribing angles and polygons inside of a circle. So inscribed, bringing something into the circle, some features on the inside of a circle. All right, I'm going to take my picture away. I suggest dating your notes especially so you can easily put them in order when that folder test comes up at the end of the semester. Okay. Hopefully you have the frame in hand. It starts with vocabulary. Ready? Here's my move. I'm going to take care of all this vocabulary at once. See text below. I'm making one note down the side that says see the text below for words for definitions described, because I'm a visual learner, and what I want to do here is draw a picture that helps me understand a couple of these concepts. It says inscribed angle, intercepted arc, subtend, inscribed polygon, circumscribed circle. Gracious. Let's draw. A feature today for you visual learners like me. Okay, so it's not going to be the best looking circle in the world, but I like Mr. Scott's technique with the water bottle lid. There's an imperfect circle. We will treat it as a perfect circle. Okay, and so in this case, I refer you to text down here. There are some decent descriptions, and if I was studying for the test the night before, I would do that. But here, I'm just going to draw this shape that's down below the page. I'm going to recreate that up here. And then I'm just going to draw some arrows for myself so I know what these features are talking about. Okay, so it has a ray going from this point through this point and an arrow. And there's a second one that goes through here. If you miss your point, you can make your point bigger. Okay, and then the picture shows this connected with a chord, these 2 points. Let's give them letters. B, A, and C. Okay, so an inscribed angle, an angle kind of trapped on the inside of a circle. Let's give ourselves an example. Angle B is inscribed. So I'm just going to draw myself a little arrow pointing at angle B. That's an inscribed angle. And they're talking about this angle here. Okay, the intercepted arc for angle B, well, angle B opens up, it shoots a ray up this way and one down this way. And if I was going to name the arc in the middle, I would name the points that contain it. So this is arc AC is the intercepted arc. And so let's draw ourselves an arrow that points at it. Different way of doing things, right? Helpful, I hope. Okay, subtend. If the endpoints of a chord or arc lie on the sides of an inscribed angle, then the chord or arc is said to subtend the angle. I looked this up on the internet, and I found a definition I like a little bit better. Subtend, generally as a word, applying to geometry, is to take up. So I'm doing this as a rewrite of a definition. To take up the side, there's a specific word I want here. Opposite. Opposite an angle or an arc. Okay, the word I want here is opposite. When you think subtend, think opposite. Here, angle B subtends arc AC. They have a mathematical relationship that we're going to talk about here in a minute. Okay. Inscribed polygon. There is a polygon inscribed in this circle. This one is a triangle. So let's name it. Triangle ABC is inscribed as a polygon, multiple-sided figure. It's got its vertices on the edge of the circle. So triangle ABC is inscribed. And then if we wanted to circumscribe circle, we want to label this circle as something that is circumscribing a shape, going around the shape. We need a name, so I'm going to give this circle a point in the middle, and I'm going to call it circle Z. Okay, and I can use a symbol for that too. Draw a dot and a circle and a Z. So how about short arrows? Both those things are in the picture. Triangle ABC is inscribed. Circle Z is inscribing, or excuse me, is circumscribing a triangle. Okay, more text on those things are below, but this is kind of how my mind works. I wanted some arrows and some visual examples of something. Okay, so moving down the page. Here's the big idea that will develop math here. The measure of an inscribed angle is 1/2 the measure of its intercepted arc. I don't always make sense out of reading the text first. I like to go to these little math sentences here. So the measure of angle ADB. Okay, here's ADB. I'm going to mark the angle. Is 1/2 the measure of the arc AB. This is the arc AB. Notice that point C there is by itself. We now have an angle projecting from the opposite side of the circle, and they have a mathematical relationship. The angle is half of the arc. Angle ADB is 1/2 the length of this arc. Whoa. I'm going to try it. I'm going to rewrite this for myself. The measure of angle ADB is equal to 1/2. You can think of that as a multiplication. The measure of arc AB. Whoa. Okay, there's some more math you can do here. If the angle's half the measure of the arc, then I can kind of flip that around for myself. Well, if I used algebra and I want to get rid of this 1/2, I want to solve here for the arc, I'm going to get rid of the 1/2 by multiplying times 2. Okay, and both of these 2's are going to cancel in algebra rules. I have to do it to both sides. Okay, so what this math leads me to is taking this, we've canceled the 2's. Okay, so we have the measure of arc AB is equal to 2 times the measure of angle ADB. If I want to find the arc, it's 2 times the angle. If I want to find the angle, it is 1/2 of the arc. I'm going to write that one more time in the notes. And this is kind of how my mind works. I'm going to break it down even simpler. 2 times the angle equals the arc opposite. Okay, so put in opposite too. 2 times the angle is equal to the arc opposite. 1/2 of the arc is equal to the angle opposite. we're going to need some math examples to go with that. They are coming. 2 times the angle gives you the arc. 1/2 of the arc gives you the angle. And we're thinking about going opposite sides of the circle. Okay. Boy, let that soak in for a second. We're going to see it in math, though. I'm going to my second page. All right. At the top of the second page is a concept that uses that again. All right. These are inscribed angles. They're talking about D and C here, where the little marks are. So ADB, that's the one centered at D, and ACB, centered at C. What they're saying with inscribed angles of a circle theorem is that both of these angles project to the same arc. And if they do, I'm just going to darken this. If these both project to the same arc across the circle, then the angles are congruent. Angle ADB is congruent to ACB. We don't know what they are, but we can say here that they are congruent because they share points in where they project. The lines cross the same place. Okay. If 2 inscribed angles of a circle intercept the same arc, then the angles are congruent. This is part of what will be puzzles to figure out in your assignment today. All right. Moving down. These are the angles inscribed in a circle. We also have polygons inscribed in a circle. And a polygon's inscribed when all of the vertices are on the edge, touch the edge of the circle. The vertices are on the edge. If I was going to put a note here, I would say see picture because I like the picture very much. See picture. This is a 1, 2, 3, 4, 5-sided figure, so it is an inscribed pentagon. It is circumscribed by a circle. That's the use of our vocabulary we're picking up here today. The pentagon is inscribed. The circle circumscribes it. Okay. Not bad, right? Not too bad. We're taking things like triangles, angles, and polygons from our past. We're sticking them inside of circles today. Here's an interesting idea. If a right triangle is inscribed in a circle, then the hypotenuse is a diameter of the circle. Okay, so let's go to this math sentence down here. The measure of angle ABC equals 90 if and only if AC is the diameter of the circle. So pay attention in problems if you see a diameter featured as part of an inscribed shape. They're saying if this guy is a 90, then this is a diameter. The chord AC is a diameter. Okay, here's the first demonstration of the concept. If this angle is 90 degrees, then the arc that it opens to, here a circle split in half, this arc AC is a semicircle is 180 degrees. And I hope that came through in your exercise earlier in the week. Semicircle is 180 degrees. It's half a circle. 90 times 2 is 180. If I had this as a measure, 180, I would divide it by 2 and find out that this angle was 90. All these are pieces that you can use to solve puzzles in the assignments and on the test that's coming up pretty soon on this unit. Last idea, then we're going to see them demonstrated, is that if you inscribe a quadrilateral, Okay, quadrilateral, 4 sides. If you inscribe a quadrilateral, the opposite angles are supplementary. Opposite angles are supplementary. So they're saying these two. Angle E and angle G are supplementary. Okay, the math sentence, I can write the same. The measure of angle E plus the measure of angle G, supplementary, means 180 degrees. That number that keeps coming up all the time this year, you can add the opposite angles. So angle F and angle D are also supplementary. You may remember 4 sides on a figure, the sum of their interior angles is 360 degrees. So this is starting to make logical sense from multiple units. And I hope you're seeing a benefit this spring. Some of the things that you remember from the past are helping you. I hope so. All right, I'm going to move on to some examples on the 3rd page. All right, here's my overall message. Treat these as puzzles. I heard it, Mr. Scott said. I think it makes you more intelligent to do puzzles. Your brain's neurology is not completely cooked. You can keep gaining intelligence, especially by doing things like puzzles and problem solving in the younger part of your life. Neurology is supposed to lock in for humans somewhere between 18 and 26. 24 is common. So what they've given me here to figure out is a puzzle. I have this image on the right, and I need to figure out the measure of a bunch of items on the left. Okay, so here we go. Let's jump in. It looks like circle N if I was going to label it. I have 3 points on the outside of the circle. This circle is circumscribing a polygon. That polygon has 3 sides, so it's a triangle. There's a triangle inscribed. Oh, I remember it. I see it. There was a concept that said if this angle opens up to what is clearly a diameter going through this middle of circle N, this is a 90 degrees, and I've just figured out number 1 by staring at this and seeing what information are they giving me. Photomath would choke on this. It doesn't know what to do. You have to stop and think about it. If this is a diameter, the principle on the previous page, inscribed right triangle theorem says that this arc is going to be 180 degrees. We have a 90 degrees here. Okay, the measure of angle C. Oh boy, here's angle C right there. Angle C opens up across the circle to this arc, AB. Got it. I think I got it. You know, there's more than one way to figure all these out. This is a triangle. It's on the middle. It's in the middle of a circle. It's still a triangle. I have a 90 and a 28, and whatever this angle is should add up to 180 degrees. Okay. There's 180 degrees as the sum of the interior angles for a triangle. So 180, subtract 90, and subtract 28. Okay. Well, that is 62 degrees. Does that make sense? Does it look like it could be? This is 180 degrees. So does this look like it could be about a third of the way around? Yeah, I can buy that. We have to figure these things out by the information given. I had a 90 and a 28, and now I've got a 62. I guess I'll try to squeeze that in here. 62 degrees. Okay. I feel like we're doing something here. I'm going to skip this for a moment. BC, it's asking for a line segment. We're going to skip that. Let's talk about the measurement of arc AC. AC is here. We just talked about math. What do I know? The angle across from it, angle B, is 28 degrees. It looks a little smaller. This looks bigger. That clues me in. I need to double this angle to get the arc measurement opposite. 2 times 28 is equal to 56 degrees. It can be that easy. Take your angle, double it, and that gives you the measurement of your arc for a situation where you have an angle inscribed. If it's on the vertex, it projects across the circle. You can take this number and double it. So let's figure out the measure of angle AB. Did we quit? Okay, recording. The measure of angle AB, or excuse me, arc AB. Okay, AB comes around this way. Aha, we could do it again. 62 degrees times 2 will give me the measurement of this arc. 62 degrees times 2 is equal to 124 degrees. I like it. 62 degrees was here at angle C. I double that to find the arc that it projects to, AB. 62 times 2 is 124. There's more than one way to figure all these out. You may discover another while you're working today. I'll quickly cover 3. They want you to just keep in mind that the Pythagorean theorem can come up. I have a right triangle here. I have one side length of, this is my short leg, 3.9. My long leg is 7.3. So I could use the Pythagorean theorem and I could solve for BC here, the hypotenuse of the triangle and the diameter of the circle. And it would look like this. 3.9 squared plus 7.3 squared is equal to my diameter. If I used a squared plus b squared equals c squared, I could just use that variable, comma c. And as Ms. Sitek pointed out, INSOLVE handles these very well, and you don't get too tripped up on the squared terms doing algebra. I think this comes to 8.3, and this is in units of length, if you'd like to check that math for yourself. Okay. 2 more helpful things to demonstrate in the bottom of the page. Name 2 pairs of congruent angles in this picture. There are many congruent angles in this picture. There are many. I'm going to go with this concept that an angle here projects to an arc across from it. Okay, so this would be 2 pairs of congruent angles. Well, ABD projects to this arc. Also, DCA projects to the same arc. We can say they are congruent. The measure of angle ABD is equal to the measure of angle DCA. Those 2 are congruent. It's happened twice in this image. This is another one. Those are congruent angles. BAC. The measure of angle BAC is equal to BAC CDB. Okay. One more concept I want to throw in. This is the two pairs they're thinking of. I see another. Here, I'm going to draw a point for myself, and I'm going to call it E. And here's a reminder that vertical angles, materials from the first semester, continue to come up during the year. You got to think of a lot of things to solve these puzzles. If two line segments cross, they make equal angles at their crossings. So I can say that the measure of angle AEB, AEB is equal to, other long side, DEC. From 4 or 5 letters, a circle, and some lines, you can make mathematically congruent statements. This is part of our puzzle working here. You can do it. Last bit is a demonstration of a quadrilateral inscribed in a circle. So this circle is circumscribing the quadrilateral. 1, 2, 3, 4 sides. The message is that these opposite angles from each other are supplementary. M, here they're saying it's in degrees, plus 65 degrees is supplementary, should be equal to 180 degrees. So if I wanted to do some algebra here, I would subtract 65 degrees from both sides. This would cancel. Rockport Middle School told me to draw the line. I'm going to bring this over, and M solved, the variable, is 115 degrees. The same variable N in degrees plus 100 equals 180 degrees. Okay, what number plus 100 gives me 180 degrees? If I talk it through in a sentence like Mr. Young does, N will be at 80 degrees. 80 plus 100 is equal to 180. Put these guys in rectangles so I see them clearly when I refer to my notes during a test, because I may use these. I may use my resources. I'm hoping you guys have picked up some today. I'll leave it back on the top here. These kinds of pictures are most interesting to me. They feel like they push my mind a little further, keep me sharp in middle age, make you all more intelligent. You'll find a assignment loaded to your Google Classroom. Good luck today. Bye for now.